Instead of static electricity, today we're going to talk about current electricity, which instead of electricity that builds up and stays, current electricity flows. And the flow of electrons through a material is an electric current. Just like the flow of water in a river is a current, the flow of electrons in a wire is also a current. Current is measured in amperes. It's named after Mr. Ampere, and it's also called amps, or abbreviated capital A. It's capital A because it's named after somebody's name. The symbol for current is the letter capital I. Go figure. I have no clue why they used I. Electric potential is another word for voltage. Now that drives me crazy, but it does help you understand voltage. Potential, voltage, what? All right, voltage is the shove that pushes the electrons through a circuit. The electrons flowing is the current. The push, the kind of electrical pressure that pushes those electrons through is the voltage. All right, a battery provides voltage. It pushes the electrons through a circuit. Voltage can also be called potential difference, electric potential difference. All right, notice they all have the word potential. Voltage is similar to potential energy. Potential energy means that when you lift something higher against the force of gravity, you have the potential to do work. You have higher potential energy because it could fall. So electrons move from an area of high electrical potential energy to an area of low electrical potential energy. Just like heat moves from hot to cold, high temperature to low temperature, wind moves from high pressure to low pressure, same with voltage, high potential energy to low potential energy, always high to low. And this provides the energy to push the electrons through the circuit and light a light bulb. Voltage is measured in volts, abbreviated V. The circuits in the US carry 120 volts. Now, your washing machine or your refrigerator might take 240 volts, but most household circuits are 120. Anything with a normal plug is 120 volts. You'll notice that your fridge or your dryer has that weird circular plug with the angles, 3 of them at an angle. That way you can't plug a normal plug in there because the wire wouldn't be able to handle that voltage. So electricity is kind of like water in a water hose. The current is the flow of electrons. All right. The voltage comes from the battery, which is like a pump for the electrons. It's like the electrical pressure pushing the electrons through. Then the resistance is what opposes the motion of the electrons. Every material has some resistance, even a metal wire. Now, metal wires obviously have far less resistance than other materials, but they still have some resistance. So the resistance is actually caused by the material the wire is made of. Here's another analogy. The voltage is like the angle of the pipe, and the current is like the flow of the water. If you have a little voltage, a little bit of a tilt, a little bit of a shove, it will produce a little current, a little water or electrons dripping through. If you have a big voltage, a big tilt, a big shove, then that will produce a big current, lots of water, lots of electrons. So that's another analogy. Finally, the width of a pipe is like the width of a wire. A thick pipe can carry lots of water because it only has a little resistance. So thick wires have less resistance because there's more room for the electrons to flow. A thin pipe has more resistance, less water can flow through. And a thin wire has more resistance because fewer electrons can fit in it to flow through. What produces the voltage? That would be a battery or a generator. Those are what pumps the electrons through a circuit. Resistance is the opposition of a material to the flow of electricity. Just like resistance to the flow of water depends on the length of the pipe, diameter of the pipe, and if the pipe is clogged or open, the resistance to the flow of electricity depends on some similar things. And by the way, resistance is measured in ohms, And the symbol for ohm is the Greek letter omega. Get it? Ohms and omega. So it looks kind of like a horseshoe turned upside down. So like we were saying, resistance to the flow of electricity depends on the material of the wire, the width of the wire, the temperature of the wire, and the length of the wire. So let's see if we can figure this out. Would a thick or a thin wire have more resistance? Remember, it's like a pipe. A thick pipe has room for lots of water. A thin pipe has room for a little bit of water. Therefore, a thick pipe has low resistance because lots of electrons can get through. Then think about a long or a short wire. Well, which is easier, traveling a long distance or traveling a short distance? Oh, a short distance is way easier, so that's less resistance. But if the electrons have to travel a long distance, they've got to fight their way through the whole wire, and that's a whole lot more resistance. That's why you always want to use the shortest wire possible to get the lowest resistance. If you're using a long wire, you have to use a thicker wire. Have you ever noticed that a 50-foot extension cord is pretty big around? That's so that there can be less resistance from the width because of the increased resistance from the distance. So that helps it not burn up the wire because it's so long. Next, hot and cold. Well, think about your computer. Is it good for your computer to get hot? No, that's very bad. It's important to keep your computer cold because if it gets too hot, it builds up a lot of resistance. So, hot wires have high resistance and cold wires have low resistance. Then finally, conductors conduct electricity and insulators prevent from conducting electricity. They don't like to conduct because they have a high resistance. So insulators have high resistance and conductors have low resistance. Now let's look at the symbols and the unit for each item. First we have voltage. It's the letter V, it stands for volts, and the symbol is V. So at least that makes it easy. Current's the weird one. The letter I means current in a formula. Current is measured in amperes or amps, which is abbreviated A. Oh well. Resistance, at least that's the letter R, that's good. It is measured in ohms, and the symbol for ohms is the Greek letter omega. Then power is P, thank goodness. Power is in watts, think about a light bulb and the wattage of your light bulb. And W is the symbol for watts. We'll be using these two equations to do some problems later on today. By the way, current is what kills someone, not voltage. So when you see a sign that says warning high voltage, it really ought to say warning high current. But we're so used to thinking of voltage as being the scary part that we wouldn't be afraid of a sign like that, and so they put warning high voltage. Now, granted, high voltage usually means high current. They have a directly proportional relationship. When the voltage goes up, the current goes up in general. However, you can make a device that has very high voltage but very low current. That'll zap the snot out of you, but it won't hurt you. For example, an electric cattle fence provides an extremely high voltage, so when you touch that fence, you get zapped, but a very low current so you don't kill the cows or the people or whatever manages to touch the fence. A capacitor is an electric device that holds and stores a charge. When that charge flows, it becomes current. So a TV has a capacitor that can hold an amp of charge, even after the TV is unplugged. So be careful. If you ever take apart a TV, make sure you know what you're doing because you could get killed even if the TV's unplugged. An example of another thing that has a capacitor is a smoke detector. I took the batteries out of my smoke detector that was beeping because the batteries were dead, and of course it was late at night, right? That's the only time it happens. And that thing still beeped with no batteries. And I'm like, oh my goodness, what's going on? And I finally figured out that there must be a capacitor inside the smoke detector. So I held down the button, it went beep, and finally that thing quit beeping because I was getting ready to take it out in the yard and take a hammer to it. All right, when you're drawing electrical circuits, you need to know the symbols that are part of the drawings. A straight line represents a wire. A line with a little opening like a door represents a switch, just like a light switch on the wall. A zigzaggy line represents a resistor. Examples of resistors include light bulbs, toaster ovens, microwaves, your fridge, a hairdryer. Basically anything that you plug in the wall and use electricity for is a resistor. They also make electronic pieces that are actually just resistors, but we won't be studying those at this time. And finally, a little long line, short line is a battery. That can be a set of one long and one short line, 2, 3, 4, however many long and short lines you want. It's still a battery. Technically, just one long and short line is a cell. Like when you have a flashlight battery, that's actually a flashlight cell because it's only one. Then when you put a bunch of cells together, that's a battery. And an example of a true battery is a car battery. It has 6 cells with 2 volts each for a total of 12 volts. So that's a true battery, whereas little size A, AA, whatever, those are actually cells rather than batteries.